Hey guys, welcome back to another video. In this video, we're going to talk about simple harmonic motion and how the equation A is equals to minus omega square x is derived. Basically, over here, x is the displacement from equilibrium, where omega is the angular frequency or angular speed, and acceleration is the acceleration of the oscillating object or the oscillator. Great. So before we dive into the derivation and the mathematical proof, let's understand what simple harmonic motion is and how do we come across this distinct or different sort of oscillation, and why is it different to any other oscillation where it does not go by the definition of SHM. So, where does simple harmonic motion come from? It is closely linked and related to circular motion or uniform circular motion. That is why we have an interesting GIF over here, which is this. If you notice, the red bob, which is going in uniform circular motion, this is changing its angle at a constant pace, meaning the angular velocity or angular frequency is constant. So let's say it's going at a constant angular velocity or frequency. Now, when it is doing that, if I draw a line, this green line, and tie it with a rope, meaning this, let's say, oh my god, this, let's say, is a rope through which no light can pass. Great. And the red bob is going in uniform circular motion. If we shine a bit of light over here, what do we see? We see a shadow of this over here, from this point to this point. Wherever this bob goes, let's say it goes over here, this will project a shadow over here. This is going to be the length of the shadow. So if it goes over here, this is going to project another shadow which is going to be of this length, And when it does that, this blue bob will be following simple harmonic motion. How does it do that? And does it really do that? We are going to see soon. So basically, when you shine a bit of light from the top and try to see the shadow, the blue bob, you see the blue bob keeps oscillating rightwards and leftwards. And it is due to the change of angle of the red bob. So let's see over here, when it is at initial position, the red bob is starting right at the middle. If it's starting right at the middle, the blue bob is right in the middle of the line. If, let's say, the red bob moves by pi by 6 radians, it will move by this distance. And let's plot this distance. Let's say it is 1 centimeter. Let's plot this over here. So at pi by 6 radians, it's moving how much? 1 centimeter. Just an arbitrary value. I don't know the value. I'm just assuming it. Next, when it moves pi by 2 radians, pi by 3 radians, meaning it goes from this to this position, it will make this length. And if you project it over here, it's going to be this much. And let's say this is 1.7 centimeter. Let's say this is 1.7 centimeter. This projection, this length, which is known as the displacement, by the way. I've written it over here. So when it was at pi by 6 rad, it was 1 centimeter. When it moved to pi by 3 rad, it became 1.7 centimeter. When it again moves to pi by 2 radian, meaning further up, it projects maximum displacement for the blue bob from this place to this place. And let's say that is 2 centimeter. And we draw it over here. We plot it over here. So we plot up till this. What on earth is that? Okay, so we plot up till this, and we see that this is coming close to a sine curve, which is pretty interesting. So if we keep plotting it, and this red bob goes from here to this new position, we can see it moves by another pi by 6 rad, from pi by 2 to plus pi by 6. You can calculate it, whatever it is, and this again moves closer, meaning it's oscillating. So let's say again the displacement is going to be 1.7 over here, 1.7. So you can see the displacement is eventually decreasing, and if you try and continue it with other positions, you will see eventually this makes a sine curve. Great. So what do we know now? From this projection of a uniform circular motion, we are getting simple harmonic motion. Which is following the simple harmonic motion? The blue bob. The blue bob is following simple harmonic motion. Because if you try to go by the definition, and if I take this direction as positive and this direction as negative, if I take, this direction as positive, this direction as negative, so for this blue bob, if I take the maximum displacement and analyze from this position, here the bob is going to accelerate towards the equilibrium. Over here acceleration is 0. So the blue bob has maximum acceleration in the middle position, in the furthest right position or the furthest left position. So if I analyze from this position, it will have an acceleration. This is not the furthest one, by the way, so for ease of understanding, let's take this one. So when it is at the furthest position, it has max acceleration. A is max. And in which direction? This is going to accelerate towards the equilibrium, which is this pink line. So if the blue bob is accelerating towards the middle, it is accelerating in this direction, and we've said towards the left is negative. So minus A is proportional to, in which direction is the blue bob compared to the equilibrium? It is in the rightwards direction. We have taken right as positive, so we say positive x. X is the displacement. So if we take the negative sign on that side, we can say A is proportional to minus x. So that is how this oscillation is simple harmonic motion, because it does go by the definition of simple harmonic motion. Okay, great. So we know that through the projection of uniform circular motion, we can get simple harmonic motion. And now, once we plot the entire curve of displacement against theta, we get a sine curve, a nice sine curve, where the maximum displacement is amplitude. So what is the amplitude? This distance. This maximum distance from equilibrium to the furthest right position or the furthest left position. Where is furthest left? Okay, I didn't draw it. So either the blue bob can be over here or the blue bob can be over here. This is red. No. Blue. Yeah. Right, blue. So it can be over here or over here, and that would have the maximum amplitude or the maximum displacement. So over here, this is A, maximum displacement from equilibrium, and this is in the y-axis over here. Y-axis is displacement. Great. For x-axis we have theta. We have drawn the curve against theta, against the change in theta of what? Of the uniform circular motion of the blue bob. Great. So we know the curve looks like a sine graph for displacement against theta. But remember, what are we trying to prove? A is proportional to minus x. Now over here, if we write the main equation, A is omega square x. For this, we need to draw it against time. Why? Because acceleration is nothing but, oh my god, right, the acceleration, if I try to prove it to you, acceleration is nothing but the derivative of velocity. dv by dt is acceleration. And what is velocity? dx by dt is velocity. So right now we have a curve which is displacement against theta. This is not going to help us in getting this main equation. This is not going to help us in getting the main equation. So what do we need to do? We need to draw the graph or curve in terms of time. If we can draw displacement against time, we can get velocity, and from velocity we can get the main equation for acceleration. So let's try and do that. Let's try and do that. All right, so for this graph, for this very graph, we know the graph is drawn as displacement against theta. So if we try to write an equation for this graph only, we can write it as, where y is the displacement and the x-axis is theta, we can say y is equals to sine theta, because it's a sine graph, and we can say that this very curve can be represented by y is equals to sine theta. Do you agree? You should, or else you should recheck your trigonometry, because if we're taking y-axis and plotting against theta and we are getting a sine curve, it is y is equals to sine theta. Great. So now if we want to manipulate it and try to bring it in terms of t, there are a few changes we need to make. First, let's change the y. Why do we want to change the y? Because in your book it is written in terms of x, meaning displacement. Y, as I've already mentioned above, is basically the displacement. It's nothing but the displacement. So don't get confused. It is the displacement, and right now we want to denote displacement as x. Why? Because the books have written it in terms of x. So only because of that we are going to write it in terms of x. In other books I've seen it is written in terms of y, which would be easier to understand. But anyways, let's write it in terms of x. Let's say let the displacement be x, meaning we are removing y and just saying the displacement is x. So we are writing x is equals to sine theta. Agreed? We have done nothing but changed y into x. Why have we done that? Just for the ease of understanding. Great. So we are taking displacement x against theta. So we can say x is equals to sine theta. Great. Now for this very graph, if it's a sine curve, right? If it's a sine curve, there must be an amplitude. And where does the amplitude fall? If y is equals to sine theta, there should be a value, an integer value in front of the sine theta, which is going to be a, or amplitude. This is this value. Let's say if it was 2 would be the amplitude. If it was 3 would be the amplitude. Since we do not know the amplitude and it's going to vary for different curves, we are going to denote it as amplitude. Y is equals to a sine theta. Y is equals to a sine theta. So we get x is equals to a sine theta. Why? Because we have changed y into x. Great. So x is equals to a sine theta. That is the equation we get as of now. Now, since this equation is in terms of theta, we want to bring it in terms of time. We know omega, if you go back to circular motion, omega is given by del theta by del t, change in angle by change in time. Great. So if we know that theta, if you make theta the subject, you're going to get omega into del t, and you plug this entire thing into theta. What do you get? You get x is equals to a sine omega del t. Omega t is basically nothing but the change in time. Since you're going to be asked, let's say this is displacement x against time, you're going to be asked what is the displacement at 2 seconds. So if this is 2 seconds and this is, let's say, 4 seconds, you're going to be asked what is the displacement at 2 seconds. So what's the change in time? It is 2 seconds. Starting from this position to this position, the change in time is 2 seconds. So you're going to count from origin to whatever position they're asking. So if they ask you for 3 seconds, this is going to be 3 seconds, you're just going to plug in 3 over here, because the change in time is 0 and 3 minus 0, which is going to be 3 seconds only. So you plug in 3 and you get the displacement in that position. Great. So we can write it as x is equals to a sine omega t. We have done nothing but substituted the value or the expression for theta. Once we do that, we get a nice equation, which is x is equals to amplitude times sine omega t. In your book, in a lot of cases, they have written amplitude as x naught. What is x naught? X naught is the same as amplitude. They just want to make your life much harder, so they have written x naught. So x naught is simply amplitude, the maximum displacement from the equilibrium position. Don't get confused. So you can write it as x is x naught sine omega t. Great. That's the equation. So this is the important equation that will help us get to acceleration. What is this equation talking about? This is the displacement equation. If you know this equation for any curve, you can find out its displacement of the oscillator at any given time. What do? You plug in the value of time. You plug in the value of time at any position. If you know the angular velocity or angular frequency, you plug the value of angular frequency, you plug the value of time, and the amplitude should be known to you, and you will get displacement for any curve. So this is the beauty of this equation. Great. So you know the arguably one of the most important equation for simple harmonic motion, at least for the beginning. So if you try to draw this curve on x and y axis, you get this beautiful sine curve, where a is the amplitude, omega is the angular frequency, time is t. Now you may wonder, how does omega t inside the parenthesis make sense? What is omega, by the way? Omega is 2 pi by time period, and t is basically the time. You know sine works with angles, right? Sine is supposed to work with angles. So where does omega t come from? Omega t is not angle, but it is. The interesting thing is omega t actually gives you the theta. The time and time gets cancelled out, and you're left with the theta. So let's say there is an object has angular frequency of 2 pi, and you want to know the position of the oscillator after 2 seconds. So you know this object is oscillating with an angular rate of 2 pi per 1 second, and you want to know the change in theta after 2 seconds. You multiply by 2 after 2 seconds, and you get equals to 4 pi. You get 4 pi. So then you input 4 pi inside the parenthesis, and you get a value of theta. This is how the equation does make sense. All right. So this is the main idea of the displacement equation. So remember, we said, where did it go? All right, I erased it. So yeah, I basically said that once you get the equation for displacement, you can differentiate it and get the equation for velocity. Once you get the equation for velocity, you can differentiate it again and get the equation for acceleration, which is the main idea of doing all this, right? So another thing, right, I forgot. This oscillation, we have assumed the red bob to start from this equilibrium position where the shadow is basically nothing but 0. So what if you start from maximum position where the shadow is maximum and giving you the maximum displacement? Then it's a cos graph. How? Because you're starting from maximum displacement, which is the amplitude, then going to 0, then going to 0, going to 0, then coming back to maximum, then coming back to 0, then coming back to 0, and then coming back to maximum, So that's how, if you change the starting position, your graph will change. So in this case, if you draw the displacement graph against time, in this case it's going to be a cos. Why? Because you're starting from a different position. You're starting from the maximum position, which is why your equation of displacement is going to be given by a cos omega t. You've changed nothing but the trig function. Why? Because you're starting with the maximum position. And you should already know this is a cos graph and this is a sine graph. So that's how we are making the equation. One equation is a sine omega t, the other is a cos omega t. Depending on how the graph is, if the graph is denoted like this, then it's a cos equation. If the graph is demonstrated like this, it's a sine equation. As simple as that. Great. Now, by the way, I've explained it in terms of uniform circular motion through the projection of uniform circular motion. You can do the same thing and prove the same entire thing using other examples, be it spring mass, be it pendulum, all examples, right? So if we look into the example of spring mass, you'll see this object, if this is equilibrium, this object is going to oscillate up, then come back down, then to equilibrium, then to maximum upwards position. Great. So if that's the case, this is definitely following simple harmonic motion. Why? Because in this case, the displacement is upwards, but of the bob, the acceleration is going to be in this direction. At this point where the maximum displacement exists, which is above the equilibrium, the acceleration is also maximum, but it's pointing towards the equilibrium because the bob will have a tendency to come back to the equilibrium and then push down. Great. So we know even in this case, the displacement and acceleration are in opposite directions. Great. So this is following simple harmonic motion. And for this graph, what's the equation going to be? Is it a cos omega t or a sine omega t? It's a sine curve, you can already see it, so it's going to be a sine omega t. Phenomenal. Now if you try to answer a question, I've made a question for this curve only. Let's say, when is the displacement a? When is the displacement a? Given that the angular frequency is pi rad per second. So the question wants to know at which time will the displacement be a? At which time will the displacement be a? Not half a, not, I don't know, quarter of a, but it wants a, the entire amplitude or the maximum displacement. So the question is asking you, when will the curve have maximum displacement? Very easy. They've given you the angular frequency. What do? You know they want the displacement as a. What do you plug in? X is equals to a. After you plug in x is equals to a, the a gets cancelled out and you're left with sine pi t. Why pi t? Because they've given omega. They've given you omega, which is pi rad per second. Once you plug in pi, you get sine pi t. Now you get the equation 1 is equals to sine pi t. What do? You take the inverse of sine, put it on either side, and you get pi t is equals to sine inverse of 1. Sine inverse of 1, you should already know, is pi by 2. Or you plug it into a calculator and get pi by 2. From this, the pi gets cancelled out. You're left with time is equals to half seconds. So you know when the time is 1 by 2 or half or 0.5, the displacement is going to be equals to the amplitude, or it's going to have maximum displacement. Great. So that's how you use the equation to solve questions from simple harmonic motion. Great. By the way, the initial problem that we had is, how does the equation come by of acceleration? So now we're going to start moving towards that direction, since we know the equation for displacement. Great.